Welcome back. We were discussing the bipolar junction transistors. Let us take the discussion forward. We will discuss in this lecture 7th on BJT amplifiers. Let us see about the transistor biasing phenomena and the small signal analysis. We have discussed biasing in very detail in lecture 6th. So the biasing of a transistor is basically a purely DC operation. When we talk about the purpose of biasing, it is to establish a Q point, which is the quiescent point for the current and voltage variation in response to the AC input signal. So in transistor, we will be having the input, which is AC. But when we talk about the biasing, it is basically what voltage we are applying in the transistor in the form of DC. So both AC and DC plays an important role in the transistor, and the quiescent point establishment in the transistor plays also an important role because it will be establishing the current and the voltage fluctuation in the transistor. We have discussed very detail about how this Q point is estimated. In applications where you required amplification of small signal voltage, for example, take the example of antenna or the microphone, there you may require the amplification because the signal is very small. Then in that case, the variation around the Q point are kept relatively small. So we will see this variation in the current and voltage need to be very small in case of the amplification process of the small signal voltage, especially in applications where we involve antenna or the microphone. Amplifiers for these AC signals are known as small signal amplifiers. The linear amplifier operation and the transistor behavior. So what is a linear amplifier? Which amplifies a signal without any distortion, providing an exact amplified replica of the input. So whatever the input we are giving, which is the AC signal, is basically having small voltage. Now we need to amplify that signal without having any form of distortion. So the replica of the input is to have the amplification without any distortion. Let us take the example of a bias transistor in the form of voltage divider. So here you have two resistors R1 and R2 which are connected as voltage divider bias in case of voltage divider bias transistor connected to the base circuit. There are two capacitors C1 and C2 which are known as the coupling capacitors. This will block the DC because the AC signal we are providing in the input, and it will prevent any change in the bias voltage at the base and the collector. So the capacitor C1 is responsible for providing any form of DC blocking for the AC supply in the base, and capacitor C2 is from the collector end. We have discussed about the voltage divider in lecture number 5. The capacitor appears as short to the signal voltage. So these capacitors C1 and C2 will be short in case of DC. Now the sinusoidal AC voltage which we are applying will cause the base voltage to vary around the DC bias condition. So the base voltage at the quiescent point will have some variation. The base current variation leads to a larger variation in the collector current due to transistor current gain. So if there is a fluctuation in IB, this will result in the variation of IC due to the current gain beta, which we have discussed because the collector current is beta times the base current. Collector voltage decreases as the collector current increases. So when the collector current will increase, then you will be having the collector voltage to decrease, and this will be vice versa operation. The collector to emitter voltage. So we will see how this collector to emitter voltage, this will vary out of phase. Now whatever the input we are giving, the collector to emitter will have been, it will be phase inversion process with the base voltage. So phase inversion, there is always a phase shifting between the base and the collector voltage. So this collector to emitter voltage, whatever we get, will be out of phase due to the phase inversion process. Let us see the base current and what is AC load line in a linear amplifier. So we can plot the collector current and collector to emitter voltage. This will give a straight line which is known as the AC load line. Now, if you have the sinusoidal voltage at the base of a transistor, this will produce a base current that varies above and below the Q point. So we have the Q point here, which is the point of operation. Now this Q point is basically giving us the point of operation of the collector to emitter voltage and the collector current. So these will be fluctuating or varying above and below the Q point along the AC load line. So you will be having fluctuation upward and the fluctuation downward. So peak to peak variation in the collector current and collector to emitter voltage are shown by the lines projected from the peaks of the base current. So here you can see the base current, there will be a fluctuation above and there will be fluctuation below. So if there is a change in the base current, obviously the collector current will also change above and below. This will also change the collector to emitter voltage but in phase inversion. AC load line differs from what we have the DC load line. The effective AC collector resistance is RL in parallel with the collector resistance, which is less than the DC collector resistance RC alone. So the resistance effective value in the AC will be less than whatever we get for the DC resistance. The distinction between this DC and AC load line we will explore in more detail when we will discuss the power amplifier. So let us see the transistor models in amplifier circuits. Why do we require models? What is the purpose? So it will represent the operation of a transistor in an amplifier using a model circuit. So we need a model circuit of the amplifier. So that will represent the operation of the transistor. Transistor model circuit utilizes internal transistor parameters to describe the operation. So we need the internal parameters of the transistor that will give you the model circuit and explain the operation of the transistor. So what are the types of parameters? First is the R parameter, which is based on the resistance value commonly used to model the transistor behavior. Other, you have the H parameter, which is the alternative system of parameters, and it will be briefly discussed. The 5 R parameters that are commonly used in bipolar junction transistor are alpha in the AC condition, which is the current gain, again collector current by emitter current. You have the beta, which is collector current by base current, and there are 3 resistances in the emitter, base and collector. So AC emitter resistance, AC base resistance, and AC collector resistance. So these are basically total 5 parameters that you have to define the R parameters for the transistor behavior. R parameters in the transistor model, if you see, so this is the resistor of the base, because this is the base terminal. You have the emitter resistance. This is emitter terminal. The collector is represented by a dependent current source, which is given by alpha into IE. So this is your collector current, and there is a resistor which is parallel to the current source. So this is the generalized R parameter model of a BJT. Now, if we want the simplified R parameter model, so the resistor of the base is very small enough to be neglected. So it will be replaced by short circuit. So we can short this resistor of the base. When we talk about the collector resistance, this one, it is of several hundred kilo ohms. It is a very high value. So it can be replaced by open circuit. So this is open circuit and this is short circuit. So if we see the resistor of the emitter looking into the emitter of a forward bias transistor, this circuit whatever we get, so here you have the emitter resistor, the base resistor is short circuited, and the other collector resistance is open circuited, and here you have the dependent current source. So collector acts as a dependent current source. Now this value is alpha times the emitter current, which is approximately equal to beta times the base current. Now alpha and beta are obviously the AC current gain. RE dash is the most important R parameter. So this parameter is the most important one, which we will see in the coming lecture. So RE dash in terms of mathematical expression is approximately equal to 25 millivolt by the emitter current. So we know the resistance is equal to voltage by current. So voltage is 25 millivolt and current we will take the emitter current. So this is the circuit of the transistor amplifier. So here you have the emitter resistance and one current source, which is a dependent current source. So this circuit can be represented like this, where the emitter resistance can be taken inside the emitter and the collector current and base current can be represented. If we draw the graph between the collector current and the base current, so you have the collector current here and base current here, the graph is non-linear. So you have the non-linear characteristic of this graph. If you want to obtain the beta value for the DC condition and the AC condition, we can obtain by collector by base current will give you the DC condition, but what is the change in the collector current by change in the base current will give you the AC condition. So here you have the change which is from the Q point. So this is your change in the base current, this is change in the collector current from the Q point that will give you the change in beta. Hybrid parameters we will discuss very briefly. Here you have the 4 hybrid parameters, which is basically the input impedance denoted by HI, voltage feedback ratio denoted by HR, forward current gain denoted by HF, and the output admittance denoted by H0. So there are certain conditions when you have output sorted, HI, in input open, output sorted, and input open. So these conditions will define the hybrid parameters. Common emitter, common base, and common collector. These are basically 3 important configuration of the amplifiers that we are going to discuss in the lecture 7b. And here you have all the H parameters which are governing these configurations. So parameters are relatively easy to measure. Hence, there is a certain relationship between H parameters and the R parameters, which are given by alpha AC condition will be equal to H of forward biased, whereas beta AC condition will be equal to H of forward emitter. So the data set often provide only common emitter H parameters, so R parameters can be obtained. So obviously whenever you see any data sheet, it will give you the H parameter only. R parameters are not given. So these has to be estimated using certain relationship of emitter resistance, the collector resistance, and the base resistance in respect of the H parameters that you have on the dataset. So these formulas are fundamental formulas that can be used to obtain the R parameters from the H parameters. So this was the basic introduction of BJT amplifiers. Coming lecture, we will see the different types of BJT amplifiers in the common emitter, common base, and common collector board. Thank you for now.